So here's the problem that we run into. There are these numbers that do not behave well. They just don't. And sorry. Okay, so there's my primality test. There's these things that are called pseudoprimes. So pseudoprimes are numbers that do not behave well. A raised to the n minus 1 is 1 mod n, but n is composite. So we just saw one of these, 1729, with a equals 2, 3, and 5, I think. It's called a pseudoprime to the base a. Pseudoprime to the base a. This is basically a number where the primality test gives you a wrong output. So this is a value of n and a value of a, where Fermat's primality test gives you the wrong output. So here's a quick list of some of the pseudoprimes to the base 2. We've got 341, 561, 645, 1105, and there's my 1729. You don't have to have these memorized. I'm just listing them out because they're interesting. So all of these, when I do 2 raised to the n minus 1, will give you 1 mod n. These are pseudoprimes to the base 2. As we saw with 1729, if you try a couple of different bases, sometimes you'll maybe get a different answer for composite, and then you can be guaranteed that your answer is correct. These are also called Poulet numbers, by the way. Some numbers are just bad for every single base. So a pseudoprime to every base is called a Carmichael number, and there is Carmichael. I don't have his first name. Sorry, I lost that one. So this is a number for which Fermat's primality test is always going to give you a wrong output for every single value of a. And I'm going to go to Wikipedia because that's the place to go, and go ahead and pull up a list of pseudoprimes, or a list of Carmichael numbers. So, list of Carmichael numbers here. All right, so 561 is actually the smallest Carmichael number, and then we've got 1105, 1729. That's interesting. Why is 1729 a Carmichael number when I got an answer out? Huh. Fermat's primality test. Well, that's weird. Let's go back to Perry and see what happened there. So if A is 7 and N is 1729, I should get that back out. I'm not sure what's going on in that case because it's telling me that 1729 is a Carmichael number, so I should get the wrong answer. I am going to have to investigate. I don't know what's going on there. That's weird. Okay, but anyway, somebody's got it?
No, is it possibly that Carmichael numbers are only for ones that aren't the factors of it?
Only for what the, oh, maybe. Like you're saying I can't use 7 because 7 is a factor of 17.
Yeah, it has to be relatively prime.
Relatively prime. That might be a possibility that's why I'm getting the wrong answer out. Yeah. So if I do like power mod of 9 to the n minus 1 and n, I should get 1 back out. Yeah, that might be what's going on. That's totally possible.
247 was the other factor, 1729. So I don't know.
Okay. And then 247 would be, I think, 13 times 19. Yeah, that's your other factor. So 13 times 19 is 247 there. Okay. All right. So Carmichael numbers. We've got a list of Carmichael numbers. So they are not super common. Sorry, I want to pull this over so I can read it. Oops. Sorry. Ugh. This is why I don't teach using technology in class. Thank you for your patience. All right, Carmichael numbers under 10,000. So here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. They're pretty rare. There's only that many less, 2163. But this is cool. There are infinitely many Carmichael numbers. So in other words, there are infinitely many values for which Fermat's primality test is going to fail. This is a really cool proof. It took a while. It took till 1994, but this is a really cool result that there are infinitely many values for which Fermat's primality test is going to fail. So, how well does Fermat's primality test work? Not great. It's okay. It's the easiest one to understand, and it's the most basic one in terms of the results that you need. The only results that you need for Fermat's primality test are Fermat's little theorem, that's it. So that's the reason that we're starting with this one, because it's the easiest to understand, it's the most basic, but it is also, I don't want to say the most potential for being wrong of all the primality tests out there, but of the three we're going to talk about, this one has the most potential for being wrong. This one will give you the most wrong answers. We're starting with it because it's easy. We're going to move on to more accurate ones, but the more accurate ones that we move on to are more complicated as well. Okay. One other thing, basic principle of primality testing, and then I think I'm going to hang on with starting the next stuff. I'm okay with shorter classes, especially since we're doing this online and it's not the best. Basic principle of primality testing, and we're going to talk next time too about where this comes up. N is an integer, and x and y are both integers, so that x squared and y squared are equal to each other mod n. But x is not plus or minus y mod n. So here's your setup, and then I'm going to have a then, which is the basic principle of primality testing in just a second. So we've got n being an integer, and we've got two integers whose squares are equal mod n, but they are not plus or minus values of each other mod n. All right. Then here's what's going on. N is composite. This is guaranteed correct for sure, because I'm outputting a value of composite. N is composite, and even better than that, I can factor n. So I can find GCD of x minus y, and n, that's going to be a factor of n. We're going to talk about why that's the case, because I think I can write on my PowerPoint slides also here. That is not what I wanted to do. So here's why, right? We need to look at x plus or minus y. That's going to be 0 mod n if you take stuff over to the other side of the equation, right? From this equation right here, if I take stuff over to the other side, and then I can do x minus y is 0 mod n. This gives me two equations. I really only want one of them. So x minus y is 0 mod n. And what that means is that x minus y divides n, or x minus y is a factor of n. So that's the reason that I can get the GCD and making that a factor of n. That works well. Okay. Basic principle of primality testing is going to come back up when we talk about other primality tests that we have. So let me stop sharing my screen. I'm going to pull you all back together. The next two primality tests that we're going to talk about are what's called the Miller-Rabin primality test. And then we are going to talk about the Solovay-Strawson primality test. So there's two more that we're going to hit. And the Solovay-Strawson primality test requires a new mathematical symbol. It's called the Jacobi symbol or the Kronecker delta symbol. So we're going to have to talk about how to evaluate that and the rules for evaluating that. Plan for the next couple of days. Wednesday is going to be talk about the Miller-Rabin primality test. Friday is going to be jump into the Kronecker delta function. And then Friday is going to be Solovay-Strawson primality test. And we'll play with each of those in Perry also and look at what works, what doesn't, when do you get a wrong output, etc. Monday then is review, and then test next week, Wednesday. Okay? How are we doing? Thumbs up, everybody good? Okay, like I said, I am okay with slightly shorter lectures because I want you to play with your homework and because I can't stand and lecture at a computer screen for 50 minutes. I just can't do it. This is not a prerequisite for anything else, so I'm okay with slightly shorter stuff going on. John, question.
Slightly unrelated, but did you just write that with your mouse? Because that was
I have a drawing tablet, so
Oh, okay.
I have a very cool stylus, and then I have a drawing tablet, which allows me to lecture live in DiffEQ and in Foundations, because otherwise I don't know how I would teach. So
I was gonna say that was very impressive mouse work. Otherwise,
no, fine point stylus. So Dr. Brown, computer science Dr. Brown, not math Dr. Brown, computer science Dr. Brown suggested getting a drawing tablet before all of this started, and I am so very glad that he did, because now I can actually teach my classes. Anybody else? Other questions, other things, questions about the paper, questions about the presentation? We have time to do that now if you've got any of those. Remember that I need to approve websites that are not .gov or something else, which you have in front of you and I don't. Anything? Questions there, Daniel?
I think the other one was articles, but can we, YouTube videos, we can check those with you too.
Sure, you
Just
can
like
check YouTube
the
videos
purpose.
with me. There might be a tutorial or something on your crypto system that you might want to use. So yeah, if you want to, you can check those with me also.
Alright, thanks.
Okay, tell me that you are not waiting until the last minute to write the paper. I'm not advocating lying, but don't wait until the last minute to write the paper. Please and thank you. Okay, all right. I will let you go. The Wednesday's PowerPoints are already posted online. Oh, I'm sorry, I know what I forgot. Flexible grading scheme. Could you please redo your flexible grading scheme? Submit that via Moodle. I think 6 of you have already. Technically, it's due by noon today, but the assignment won't close. So if you could get that submitted on Moodle, that would be good, because then I can start the process of recomputing grades. Please and thank you. Okay, enjoy a little bit of extra time. I think that might be potentially the norm here. We'll see. And I'll see you guys on Wednesday. Thank you. Have a good day.